So, we are going to end the discussion on the development of the theory in this case by giving few more tips. So, let me just highlight a few more tips. So, ways to improve the Euler's or the numerical solution, to the Euler-Lagrange method. Well, some of the natural tips would be to increase or make the grid finer, or to increase the number of grid points, or so that is the standard suggestion, but some of the non-standard suggestions are to use better quadrature rules. Here we have just used rectangle rule to change the integral into summation. So, we could use better numerical quadrature. Some of the quadratures available are trapezoidal. We could use trapezoidal quadrature, or we could use Simpson's rule, right, or we could use even higher order quadrature like the Romberg rule, right, or we could use adaptive grids, right. So far the example I have shown is for a uniform grid. We could also use adaptive grids. Grids will become finer where the function changes rapidly, right, and non-uniform or adaptive grids. Okay. So, more details can be found in this textbook. So, students are asked to refer to this textbook for more details on the numerical solutions of Euler-Lagrange via the Euler's and other higher order methods. This book has the title Calculus of Variations with applications in physics and engineering by Robert Weinstock. Okay. So, what we have is the following. So, we see that let us look at another method or the numerical solution. The method that I intend to highlight is the Ritz method. Okay, the Ritz method. Now, what exactly is this method? This method tells us that we could, rather than approximating by taking the values of the function at finite number of grid points, we could use a set of basis function to approximate our extremum function. So, we could use a set of orthogonal basis function and expand our functional in terms of the basis function, right. So, the idea is as follows. We are going to approximate our variable. Using family of linearly independent functions. We are going to approximate our variable using family of linearly independent function, right. And let us say our family is as follows: phi I from 0 to n, right, where our function is yn of x. So, I am going to approximate y. So, y, the unknown of the problem, is going to be approximated by yn, which is a linear combination of phi i's. So, C1 phi 1 of x, this is also a function of x, and so on, plus Cn phi n of x, right. Okay. So, we see that. So, then again this sort of an approximation again reduces the problem from the functional optimization to the problem of function optimization, where the unknowns now are these constants C1 to Cn, right. So what I said is, well, let me call this as point number 1. So point number 2 is we reduce the problem, into standard multivariate minimization problem. Standard multivariate minimization problem for unknowns Ci's, right. So what we do is, so the unknowns now after applying the approximation in the previous slide will be Ci's, and all we do is differentiate our function, that is, we differentiate our function with respect to the Ci's and set it equal to 0, right, where my function is now an approximate function of yn. So y has been approximated by yn, right. So which means this particular quantity to begin with was an integral. So this was a functional of this integral of this following quantity, and this is now a function of the variable C1 to Cn. Okay. So then, well, let me just write down all the points, and I am going to highlight this method with an example. So further we choose in our choice of phi i's, notice that I have started with phi 0 and I have started, well, with a coefficient 1, and I have phi 1 to phi n. So we choose phi 0 of x such that the boundary conditions are satisfied, right. You choose phi 0 of x such that the boundary condition is satisfied, and further we choose phi j's of x such that with homogeneous boundary conditions, which means that we choose our phi j's such that phi j of x naught is phi j of x 1 is equal to 0, where j is from 1 to n, the rest of the phi j's, right. And then note that phi j's could be, let me call this as 4. So phi j's could be from the standard set of orthogonal functions, like power series or polynomials, or it could be the trig functions like sine and cos. It could also be the Bessel function, right, and so on and so forth. Okay. So then, so we assume so a little bit of analysis before we look at some examples. Let us say that y is the extremal to the problem, at hand. We assume that without loss of generality, the extremal we are talking is minimum, right. So in that case, we have that the value of the functional f of y will be less than f of y hat, where y hat is the perturbation of y, right, where y hat is within, let us say, within epsilon neighborhood of y, right, close enough to y. So then, well, so what I want to show here is that the value of the functional, which is the value of the function that we get from the Ritz method will be, if it is very close to the original extremal found from the Euler-Lagrange, then the value of the function from the Ritz method will give an upper bound to the value of the functional or the exact value of the functional, right. So, what I just said is the following. So, what I have is, so f of y, so we assume that our approximate solution, our approximate function y n is inside the epsilon neighborhood of y. So, which means the approximation from the Ritz method is sufficiently close enough to the exact extremal, right. So, in that case what we have is f of y is less than equal to f of y n, which is the value obtained by evaluating the values of these CIs, right. So, well, let me call this as f n because we are approximating up to n terms. So, as I just said, the approximation gives an upper bound, as we can see from here. Okay. So, if we were to, so care must be taken for a careful choice of phi i's, and not only that, the higher the value of the phi i's, we expect that the closer is the approximate solution to the exact solution, right. So, let us look at an example. The example says, find the extremal of f of y. Well, we look at the same functional y prime square by 2 plus y square by 2 minus y, right, dx, with y 0 is equal to y 1 is equal to 0. Okay. So, I know that my Euler-Lagrange method, my EL equation reduced to the following ODE for this problem, and well, let us go back to few slides to check what was the solution. We get the following ODE, right. So, we get the following ODE, and now if we were, so we are in a position that whatever solution that we get via the Ritz method, we can check it with the solution of the Euler-Lagrange to see how close is it to the exact solution. Okay. So, if we were to use the Ritz method, so let us say this is the solution. The Ritz method shows that this is y n of x is phi 0 of x plus summation C I phi I of x, where I is from 1 to n. So, we are going to take phi 0 of x to be identically 0, because by taking this value, the y n's immediately are going to satisfy the boundary condition, and we take phi i's I from 1 to n as this following polynomial functions. So, this is what we choose in as our basis function. It can be shown that these are linearly independent basis functions. Okay. So, all we need are linearly independent basis functions. So, then let us look at a simple approximation. So, we are going to approximate y with y1, which is also equal to C1 times phi 1. So, there is just one unknown to be found, which is C1, which is also equal to C1 times x times 1 minus x by plugging in I equal to 1. So, then in that case f1 of C1 is nothing but f of y1, and this is also equal to the integral from 0 to 1. I am just plugging in, instead of y I am plugging in y1. We see that this is also equal to C1 square 1 minus 2x, right. So, phi 1 is this quantity, and I can immediately from here get that phi 1 derivative of phi 1 is 1 minus 2x, right, where phi 1 is x times 1 minus x. So, I get the following expression now. So, C1 square by 2 1 minus 2x whole square plus C1 square by 2 x square 1 minus x whole square minus C1 x 1 minus x dx. Okay. So, then what we get is that this is also equal to after opening up all the squares, we are going to get that this is C1 square by 2 times the integral 0 to 1 minus 4x plus 5x square minus x to the power 4 dx plus C1 integral 0 to 1 minus x plus x square dx, right. So, then once we perform all the necessary integration, I am going to get the following result, that f of f1 of C1 comes out to be, after doing all the necessary integration, C1 square by 2 times 11 over 30 minus C1 by 6. So, we solve for C1. We solve for C1 to see that by taking the derivative of f1 with respect to C1 and setting equal to 0, standard multivariate minimization argument or optimization argument, we see that this is also equal to 11 C1 by 30 minus 1 by 6 is equal to 0, or I get that C1 is equal to 5 by 11, right. Okay. So, then from here I get that my solution y1 is C1 times phi 1, which is this, right, and this is my approximate extremal that we have obtained using the Ritz method. We can check that the value of the functional evaluated at y1 is coming out to be this following constant, which is minus this quantity, right, and by the analysis that I have just shown few slides back, this is the upper bound, of the solution to the Euler-Lagrange, equation, right, which was highlighted few slides back. Okay. Okay. So, before we move on, I just want to highlight how does this approximate solution compares with the exact solution. So, if we were to plot y versus x, the exact solution is as follows. So, this is the y exact, or this is also equal to the y obtained from the Euler-Lagrange method, and the solution that we obtained above right, which is my y1, which is this particular solution, is quite close to the exact solution. So, even with this approximation with one basis function gives us close enough approximation to the exact solution. Okay. So, alternatively, well, the choice of phi is ours, the choice of the basis function is ours, and sometimes the choice is good, while some other times the choice is poor, right. So let us look at another choice of the same function. So alternatively, suppose we were to choose the following basis function. Suppose we were to choose phi 1 equal to sin pi x, right. So notice that phi 1 at 0 is phi 1 at 1 is also 0, right. So a similar exercise of finding the approximate solution leads us to y 1 equal to the C 1 phi 1 comes out to be 4 by pi times pi square plus 1 times sin pi x. Okay. So use the Ritz method and we will see that the solution comes out to be the following. And if we were to now plot the exact solution with respect to, let us say, the approximate solution. So let us say this is my exact solution. The approximate solution in this case is poorer. Okay. So which means in this case we have a poor choice of phi 1, right. So this phi 1 is not a good choice. So the moral of the exercise that we have done so far is that the choice of the basis function phi i's matter, right. So I am not going to go into more detail as to what sort of phi i's will be suitable for what sort of functional, but I am going to definitely give a reference which talks in depth about the choice of this Ritz basis function. So first of all, the choice of phi i's matter, and also the approximation becomes better using larger families of phi i's. That is, this advice is irrespective of the method, whether we use Euler, whether we use Ritz method or another method that we are going to describe shortly. So use larger and larger family to get better approximation. Okay. So let us look at an example. So I am going to highlight an example. So I am going to solve the same catenary problem via the Ritz method, Okay. So my functional, which is the potential energy functional in the catenary problem, is as follows: 0 to, well, x0 to x1 y times square root of 1 plus y prime square dx, right. And I see that this is with the boundary condition y of minus 1. So I choose my x0 to be minus 1 and x1 to be 1. So y of minus 1 is equal to y of 1. Let us say this is also equal to some y0, right. So what we have done, we are solving a symmetric problem where the height of the extremal is the same at both the boundary points. Okay. So we all know over the discourse of the last few lectures that the solution to the catenary problem via the Euler-Lagrange equation is in the following form: y of x is equal to C1 cos hyperbolic x by C1, right. And y1, let us say that let us assume further that our y0 is 2. So y1 and y minus 1 is equal to 2, right. We are assuming some value, some numerical value. So that gives my 2 values of C1. So we already know the solution. When we impose the boundary condition y minus 1 equal to y1 equal to 2, we get 2 values of C1. C1 is either 0.47 or C1 is also 1.697. So we get 2 values of C1, right. We have already discussed that if your y is above a certain critical value, I am going to get two solutions, right, not necessarily both of them minima. Okay. So, in that case, well we can immediately see which one is minima or which one is maxima. So, at the value C1 is equal to 0.47, I see that F1 at C1, well, the value of the functional f of y comes out to be this quantity 4.36. So, we can just plug in C1 and plug the extremal y here into the functional of our potential energy function, and we see that. So, let me use the same notation Wg of y, it comes out to be this value, and at C1 equal to the other value, I see that my potential energy functional comes out to be the following quantity. So, this one is the minima and this one is the case of maxima, right. Okay. So, let us see what happens when we find the solution via the Ritz method. Okay. So, we see we are going to in our Ritz method we are going to approximate via polynomial functions this time, polynomial function. Okay. So, I am going to say that my y of x is approximately equal to yn of x, and yn is a0 plus a1 of x, right, and so on, plus a2 of x square and so on, right. Okay. Now, before we move ahead, we also know that the problem is symmetric. We stated that to begin with, which means that the solution that we are assuming must also be an even function to account for the symmetry, right. So, which means due to symmetry of the boundary condition, y of x is even, right, due to symmetry of the boundary condition y of x is an even function. So, which means that my odd coefficients a1 is equal to a3 and so on, they are all 0, right. Okay. So, let us let us now approximate y of x by y2 of x, which is nothing but a0 plus a1 x square or a2 x square, a1 is already 0, right. So, let us use the least order approximation and see how does the Ritz method compares, right. So, further we know that y1 y at 1 is also equal to y0. We have taken y0 equal to 2, which we will use later on. So, this is also equal to 2. In fact, let me plug the value here. So, this means that y of x now is, I can eliminate with this boundary condition, I can eliminate one of the constants a2. So, this becomes a0 plus 2 minus a0 times x square, right. Okay. So, then what I have is the following. So, I have y of x. So, similarly, I can find y prime of x. My y prime of x comes out to be, we differentiate this 2 times 2 minus a naught x, right. So, then I substitute all these into my functional of w p of y, the functional that I had, and find out the expression. So, substitute, let me call this entire expression, the set of these two expression as 1. So, we substitute 1 into our functional w p of y and integrate. We can very clearly integrate with respect to the variable x, right. The variable x can be integrated out, and we are going to be left out with a function of one variable a naught, right. It is easier said than done, because we will see that this function is very complicated, right. So, integrate to get w of a naught, wp at a naught, right. We see that, well, let me just show you that the function that is generated here by showing you some of the terms. So, these terms are generated from the software Maple. So, Maple gives, when we feed all these approximations into the functional in the software Maple, we see that my expression wp of a naught is the following. So, let me write few terms. In fact, I am never going to complete writing all the terms. So, let me just show what is the complexity that we have. So, this is the quantity, and then plus minus 4 log natural log of 2 minus 1 minus natural log of 4 minus 4 a naught plus a naught square, okay, and that completes this bracket, and minus square root pi times dot dot dot. So, let me not even write all these terms, just tell that there are about 428 terms. So, notice that the complexity that we have. So, what I am trying to show here is finding the optimum solution of WP, or finding the optimal value of a naught by hand is almost impossible, right. So, we cannot just take the first derivative and set it equal to 0 and find the solution analytically. However, if we feed this entire expression in the software itself and draw the figure WP of a naught versus a naught, we can see where is the maximum or the minimum. So, when we do that, so we plot numerically, we see. So, let me show the plot in the next page. We plot numerically and highlight that WP of a naught versus a naught. We see that we get the following function. We get the following curve, where we obtain this maxima at a naught equal to 0.41 and the minima is obtained at a naught equal to 1.69. Okay. So, this is my a naught axis. So, we can see that the local min is at a naught equal to 1.69, and the local compare the local min for C1, which was at 1.697 for the exact function to the, or the exact solution to the Euler Lagrange equation, right. And the local max that we get here is a naught equal to at 0.41, and again compare it with the local max at C1 equal to 0.47. So, it seems that in this case my minimum and the maximum are quite accurately captured by the Ritz method of the original extremal, right. So, this question that we have to ask, when is this case always true, or what I am asking is the following. What I am asking is the nature of the approximate extrema identically equal to the exact extrema, right. So, we saw the exact solution, the solution to the Euler Lagrange, and the solution obtained by the Ritz method, and we saw that the maxima and the minima, they are almost identically equal. So, this question is the nature of the approximate extrema equal to the exact extrema always? Is this always true? So, the answer to this is, it depends on how good is the approximation, right. So, the answer to this is, if I have that the approximation, if the approximation is near, when I say near, the near is in terms of a certain norm. So, near to the actual extrema, right, if the approximate and further there is no other extrema, nearby, right. So, we do not have multiple solutions to the Euler-Lagrange equation, otherwise the approximation to the via the Ritz method might give erroneous answers. And finally, the functional that we are optimizing is smooth, so that the derivatives exists, then the answer is yes. So, then yes, that is the type of approximate extrema is identically equal to the exact extrema. Okay. Okay. So, that completes this particular example, completes the discussion of the Ritz method. The students are asked, I am going to provide a reference towards the end, and the students are asked to solve more examples via the reference as well as our homework modules and the tutorials.